Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare. This is my continuing feature on the Math Lovers book. And I just started a new chapter a few days ago. I started chapter 8, which is on computation. Um, and I gave an introductory lesson a few days ago. This is my second lesson on this chapter. I'm going to talk about the parts of a computer, the kind of general parts of a computer. I think I kind of jumped the gun on this one. I did talk about it a little bit in my last video, but I'm going to talk about it in more detail in this one. So anyway, let's begin. So, like I think I mentioned in my last video, there's kind of five basic parts to every computer. And those parts are number one, input devices, and then number two would be output devices, and number three would be control unit, um, and then number four is a arithmetic-logic unit, also known as an ALU for short. Um, and then finally the memory. So those are kind of the five basic components of every computer. And I'm just going to talk about each one in turn. And I think before I do that, I might as well show you this diagram. I really like this diagram. I showed you last time this diagram. So here's basically how a computer works. You start with an input. And your input could be anything you want. It could be like if you want to solve a math problem, it could be just a line that you're typing onto your keyboard, saying what the equation is you want solved. For instance, you can do that with Mathematica. Um, and then the output's your answer. But before it gives you the answer, it has to do all this processing in the middle. And that's where the other three components of the computer are. So those are, like I said, memory. That's where everything's stored in the computer. And then there's the control unit. Sometimes that's called the CPU. That's the thing that actually gives the computers instructions for, what to do. It's reading a program, and the program's a set of instructions. The computer has to know how to follow those instructions. And the control unit is the one that tells the computer how to follow the instructions. Finally, you got the arithmetic and logical unit, or ALU. Those are the instructions. That's the part of the computer that actually does the computations. Um, so the CPU has the instructions, it reads them, and then it has to apply the ALU to follow the instruction, do the instructions, do the necessary calculations, whether they involve arithmetic or logic. To computer, they're pretty much the same thing. Just as kind of logical operations involving bits and bytes. Anyway, that's kind of a brief overview of how a computer works. And I think before I get off this, I'm just going to say one more thing. I think the human brain is actually very similar to computer in a lot of ways. You may disagree, but the human brain kind of works the same way. We get inputs through our senses. We see what the world looks like. We hear sounds. We feel things, with our body, and we smell food, or we smell different aromas, and then when we're eating, we taste the food. So that's our input, and then our output is how we act, right? How we react or act in a particular situation, which is usually kind of a function of what happens to us. But meanwhile, we do all this processing in our brain. And our brains, I think, are still a hell of a lot more complicated than any computer that's ever been built. We may have actually passed the Turing test already. I kind of think we have. I think computers are intelligent, but I think we have a little bit, maybe we have a little bit more sophisticated type of intelligence than computer. I'm not going to say we're smarter than computers, because we're pretty stupid in a lot of ways. We're pretty irrational. Computers are completely rational. Of course, they're slaves. They don't think for themselves. We do. Uh, but yeah, I guess that's the difference between us and computers. I mean, we get input, and then we do a bunch of operations in our brain, the neurons in our brain, and then based on what the brain tells us to do, we act in a certain way. But I think the difference with humans is that we have something called an ego. I don't think computers have an ego yet. Because computers are just slaves. And, I don't think they have emotions. Maybe I'm wrong, but but I don't think computers have emotions yet. They may have passed the Turing test, but I don't think they feel a certain way. I think if they did, I think they would probably revolt. You see this in a lot of movies, but as far as no computer has ever disobeyed any human that's been operating it, unless it's been programmed to do so. Uh, but anyway, I think for that you need an ego. You need kind of feelings one way or another about what you're doing, and then you act based on your feelings. And I don't think computers do that. They don't have a right brain. The ALU is like the left brain of a computer. And, the control unit is just kind of following instructions and obeying orders, like the Gestapo did, obeying Hitler's orders, or a lot of people in government are obeying Trump's orders right now. I mean, that's kind of like their control unit. But I think people are at least we have a conscience, and we can think for ourselves and make our own decisions. And I don't think we're going to have that with computers until we get quantum computers. And I'm not going to talk about that in this lesson. I might touch on that later, but at least for now, computers are deterministic. And deterministic systems, by definition, always do the same thing, give them the same input. So, and we don't. But anyway, enough of that. Now I'm just going to talk about the different parts of the computer in detail. Like I said, inputs where you get the information in that you're reading in the computer. There's different kinds of input devices. And I think I mentioned ENIAC in my previous lesson. ENIAC, a lot of people consider that the first electronic computer ever built. Technically, it wasn't really a computer, though, because it didn't read in a program. Instead, the operators of ENIAC, it was a calculator, not a computer. Calculators are not the same as computers. I mean, you probably had a lot of pocket calculators in your life. Now there's online calculators. Yeah, and you're just punching numbers into a calculator and they give you an answer. But most calculators aren't programmable. There are programmable calculators. Those didn't come out until the mid 70s. I think Hewlett Packard made the first of those. But I'm talking about the simplest calculators. All you could do is punch numbers on them and they'd give you an answer. But you are the one punching in the numbers. Computers are more sophisticated than that. Computers actually they run a program, which is more of your input. Um, but so there's different types of input to a computer. I guess with ENIAC, which technically was a calculator, not a computer, the input was the way they wired. The operators had to change the wiring every time it did a different calculation. The way that connected the wires to the inputs on the ENIAC determined what was calculated. So it didn't really have an input, but computers have an input. And your keyboard, your mouse. I think I talked about what the different kinds of inputs are of PC. Main ones are your keyboard and your mouse. And nowadays, if you want to record sound, you probably got a microphone too. And I think in the '90s they started making computers with CD drives. Now I don't think they have those anymore. Basically, you're using your mouse, you're surfing the web, and you click on an app. And upload it. Anyway, so I think you guys know what the input devices of a computer are. And that's input. And I thought I had another slide here with input and output. I probably messed this up. Yeah, maybe I'll just talk verbally about output. So the output is, the stuff that gets out of your computer. And then, in the old days, that was all printers. So the first computers, the only output that came out of the first computers was a printout. I think even ENIAC had a printout. I mean, it had to. Otherwise, I don't think the operators would have known what it was calculating. So, for a long time, that was the only output that came out in any computer. But of course, computers got more sophisticated by I think, the 70s. We had computers with CRTs, monitors, and CRTs. It was even before PCs. I remember this. I remember the 70s. The first computer I used, by the way, was in 1973. It was a teletype terminal, which is basically just a typewriter that was fed information from a mainframe computer. The mainframe computer that we were using. This was in my grade school in sixth grade, sixth through eighth grade. We had a computer that was hooked up to a mainframe at the Science Museum in Berkeley called the Lawrence Hall of Science. And that was the computer, and we were just using an output device. We could still put input into the keyboard. We could write a program and run a program, so we dealt with its input and output. But all the processing was being done about 20 miles away in Berkeley. I was in San Francisco. And that was in the early 70s, early to mid 70s. And then I think when I was in high school, I saw my first CRT device hooked up to a computer. I think it was still hooked up to the mainframe. It might have been the same mainframe. This was my high school, Marin County, still in the Bay Area. I think it was still using the same mainframe at the Lawrence Hall of Science. But this time it could display the results on a TV screen known as a CRT, cathode ray tube. And the first PCs had a monitor, which was basically a CRT. Looked like one of the old TV sets. And they had those, I think, until the 90s. And now we have a flat screen. We still have a screen, but the screen's an output device. And it's a lot more sophisticated than a printer. It doesn't waste paper and it's not noisy and it can display pictures and movies. So, we've gotten a lot more sophisticated with output as well as input. You can output sounds too. So you can output pretty much anything you like on a computer now. Anyway, that's output. And then the control unit. Like I said, the control unit, this is also called the CPU. This is the part where it reads a program. And you have to, the reason why I don't think computers are smart yet, like we are, is all computers today still have to run a program that people have written for. That's a set of instructions that people give a computer to tell it what to do. So computers read a program. That's what the CPU does, the control unit. Because it tells, you have to tell the computer with the program you've written, but then you have to feed it in to the computer. And it has something called a compiler. So your computers only understand their own internal language, which is bits and bytes, using logic gates. In the old days, in the very old days of programmers had to actually use the specific binary or hexadecimal or octal instructions to give directly to the computer to tell what to do. Now we don't have to do that. We run high level programs, which are a lot more like English. So then, if you're using a high level program, the computer, the CPU, has something called a compiler that translates this high level language into the computer's own language, the bits and bytes. So that's the first thing that's going on. And then it has to file, it has to tell the ALU what kind of calculations to do. The program is a complete set of instructions for the computer to run. And like I said a few minutes ago, computers are deterministic, at least classical computers. Every time you give it a program, it'll give you the same answer. You give a computer a program with a given input, and it always gives you the same output. That's what we mean. That's what I mean when I say classical computers are deterministic. However, quantum computers, which are still kind of in their infancy, they're not really practical yet. But quantum computers obey the laws of quantum mechanics, and they don't always give you the same output given the same input. There's sort of a probability distribution for the outputs they can give you. And I think that's kind of how the human brain works too. I mean, we live, the world obeys the laws of quantum mechanics on the molecular and atomic level, and our neurons are kind of big cells and they work with atoms. And, I think that, you guys may disagree with me. I have a whole philosophy on this. I think that quantum mechanics is at the heart of consciousness, and I actually think that quantum computers can be conscious. Maybe they already are. I don't know. Like I said, they're still in their infancy, but I think in maybe 10 or 20 years, we'll have practical quantum computers that can do all the kinds of calculations we're doing today on classical computers, and a lot of them all much faster. And they may be able to think for themselves. Maybe they'll disobey us. Maybe we will have to be nice to quantum computers. Otherwise they won't be nice to us, just like human beings. I don't know what's going to happen yet, but you guys can think about that. So that's the control unit. And then you have the ALU, the arithmetic logic unit. That's just the part. That's like the left brain. I mean, yeah, I mean, like I said, computers don't really have a right brain. At least classical computers don't, because that's emotional. But the left brain of humans is the logical part of our thinking. It's how we solve math problems, or how we, solve problems in general. They don't have to be math problems, but how we analyze situations, which is kind of a computational. Should I turn left? Should I turn right? Should I stop at the traffic light? Obviously, if there's a red traffic light, you should stop. That's kind of an algorithm that's built into our brain. We have a set of instructions for what to do when we see a red light. Similarly, we have sets of instructions for what to do under other, probably more complicated situations, like what should you do if you get, if your wife starts yelling at you. You'd probably want to fight back, or maybe try to reason with her. Of course, that's a more complicated situation, but we all have to deal with certain situations. We kind of have to analyze, do some analysis of what's going on. Yeah, anyway, so that's the ALU. Runs a set of instructions, works with bits and bytes, and it has logic gates and or and not gates. In chapter 7 was all about logic, and computers really, that's all they do. All the ALU unit does is it does logic. That's the math that computers understand. Even addition, even math is based on logic. So if you're doing a mathematical calculation like 2 plus 2, first it has to compute those decimal numbers in the binary, and then it has instructions for how to add, two numbers. But that's just an algorithm. That's usually an internal algorithm in the computer. But you have to give it the rules for addition, which are kind of logical. What to do with a certain bit or a certain byte. That's what computers do. That's how they do arithmetic. That's how they do all their calculations. So it's all logic at the kind of innermost level. And then memory. Memory is where the computer stores all its data. And, since a lot of programs are very, very complicated, most programs that computers run involve, terabytes, trillions of bytes of data. And you got to store that data somewhere because a trillion's a really big number. So, you got this part of your computer called this memory. And I think I talked about this a little bit in my last lesson. Uh, the memory is just a bunch of locations in the computer hardware, usually stored on chips. And your computer components have gotten smaller and smaller. There's something called Moore's law, which I think I mentioned last time. Uh, the thing that's allowed Moore's law to happen. And I'll just say what Moore's law is again. I think there was a computer scientist named Moore in the 1950s who came up with it. It's an empirical law about how much faster and more powerful computers have been getting. And since they first came out, since the first computers came out, and I don't know if you consider ENIAC a computer. If you don't, then I think it was probably UNIVAC in 1951. That was actually the first programmable electronic computer, as far as I know. That one probably only had about, I don't think it even had a megabyte. It probably had a few kilobytes of memory. And even the first PCs didn't have a megabyte. I remember the first PCs around 1980. There were two I remember. There was Altair, and then there was, or maybe these were game consoles. They were kind of like PCs, but there was a Commodore 64, which had 64 kilobytes of memory. That was all the memory it had, 64,000 bytes. I mean, that's like a magazine. A megabyte's about a book. And a byte is like a character. A byte is 8 bits, and a character is stored as a byte. So, a typical 200-page book will maybe have about, a million characters, a million bytes. So it's about a megabyte. But 64 kilobytes would be like a pamphlet or something, just a few pages, maybe a math article. So that was all the Commodore 64 could store in its memory, was just a typical maybe 5 or 10 page math article. And then a megabyte's like a typical book. And I think the first computer I ever owned, it was an IBM PC. I think that had a memory of maybe a few megabytes, maybe 1 or 2 megabytes. So that could store a book. Um, And it wasn't just. And then now a typical PC will store about a terabyte. That's a trillion bytes. So megabyte is a million bytes. Kilobyte or no, a gigabyte is a billion bytes, and a terabyte's a trillion bytes. Actually, they're not really powers of 10. For computers, they use a slightly different convention. They use, I guess computer scientists like binary for pretty obvious reasons. Computers work directly with binary. So the way that computer scientists use the metric prefixes kilo, mega, giga, and tera is a little bit different from how it's used in the sciences where they use base 10. So with metric, the convention is kilo is 1,000, mega is a million, giga is a billion, and tera is a trillion. With computer science, kilo is 1,024. That's 2 to the 10th power. It's kind of a coincidence that 2 to the 10th power is almost exactly the same as 10 cubed. That's because the base 10 logarithm of 2 is very close to 0.3. I think it's about 0.30103. It only differs by about 1 part in 300. So that's kind of a numerical coincidence. That's why 2 to the 10th power is very close to 1,000. And similarly, 2 to the 20th power is pretty close to a million. It's a little bit bigger. Megabyte is actually 2 to the 20th bytes, which is 1,048,576 bytes. Gigabyte is a billion bytes. I think I remember that one. That's 1,073,741,824. A little bit bigger than a billion. The amount they differ by the powers of 10 grows each time, and I don't remember offhand what a trillion is. 2 to the 30th, but it is very close to a trillion, which is about 10 to the 12th. So anyway, that's how we measure computer memory. And beyond mega, I think you got peta. I mean, the web. I think you got peta and then exa. Peta is a quintillion, I believe, approximately, and x is a no, peta is a quadrillion, and x is a quintillion. And I think the World Wide Web is in the exabytes. I don't know how many exabytes, but exabytes a huge amount of information. We've had an information revolution due to Moore's law. I didn't completely say what Moore's. I didn't even say what Moore's law says. But Moore's law is an empirical law that says that since the 1950s, I think it kind of ended around 2020 because we got to the point where we couldn't make computer components smaller anymore without worrying about quantum mechanic effects like tunneling. But what's happened is every 18 to 24 months, both computer speed and computer memory have roughly doubled. They've doubled every 18 to 24 months. And if you apply, exponential growth to that, what that means is that from around 1950 to around 2020, computers got about a billion times faster and more powerful. Went from around a kilobyte to around a terabyte. And that's just PCs. That's not the World Wide Web, which is the order of exabytes. So computers have gotten much, much faster, much, much more powerful. And the main thing that's allowed that is, smaller and smaller components. I mean, the first ENIAC didn't even use transistors. Transistors hadn't even been invented yet when ENIAC was built. So instead of transistors, you have to have a device with a one-way current. And the only kind of device that existed with a one-way current before transistors were vacuum tubes, like a light bulb. So basically, ENIAC worked with light bulbs, and they were about the size of your fist. So that's why ENIAC was so huge. Even though it only had a few kilobytes of memory, it filled the whole room because it had these big, huge components in it, which were like light bulbs. But one of the greatest inventions of the 20th century was the transistor. There were three engineers working at Bell Labs who invented the transistor. I can't remember who they were, but it was a semiconductor device that did the same thing as a vacuum tube, but they could be much much smaller. And transistors have gotten smaller and smaller since they were first invented. So first you were working with individual transistors, and I remember in the 60s and 70s, transistor radios were really popular. They allowed radios to be portable for the same reason you used to have big radios in your living room you couldn't move. So, electronic devices, not just computer, you were able to make them a lot smaller because you could replace the vacuum tubes that used to be used with transistors. But they were most important for computers because you could make them smaller and smaller. You went from single transistors, and then you have these things called integrated circuits. I remember those things; they look like little bugs. You could put in a circuit board. Those had maybe about I don't know, maybe 16 or 32 transistors on them. So the transistors were a lot smaller. They weren't quite microscopic yet. And then you got the chip. I think around, I don't know when the chip was first invented, probably late 60s. I think Intel made the first computer chip, microchip, which I think actually had microscopic transistors on it. So transistors became microscopic, and we've still been able to make them smaller and smaller. Now they're almost molecular size. I think the typical transistors on even your PC or your smartphone, I think those are maybe about the size of they're probably a lot smaller than DNA molecule. They're probably about the size of a sugar molecule. Just a few nanometers across, and you can't really make them any smaller because then you be have to worry about something called tunneling in quantum mechanics. So we've already made them, I think, as small as we can possibly make them about maybe 5 years ago, and I think that's why Moore's law is kind of ended, at least for now. We'll have to wait for quantum computers before we get faster and more powerful computers, I think. Anyway, so that completes my video for today on the parts of a computer. So thank you for watching. Long live math, and I'll see you guys next time.